Good morning. Today, I'd like to make a summary of everything I've been talking about in the face-to-face class over the last week to 2 weeks. This is going to be a summary of what we have figured out and how to actually do the calculations. I'm going to omit all the theory development because I have separate videos that the interested can view on those topics. The problem is this. Given n plus 1 data points, indexed 0 through n, of a possibly unknown function, find a polynomial p of x so that whenever you put one of the x's from the data set into polynomial p, the result is the appropriate function value to go with that x number. P will be called an interpolating polynomial for function f. We've figured out a number of things about these sort of polynomials. The first thing we figured out is not only can you do this, but there is exactly one polynomial of degree n or less that will solve our problem. As will be mentioned later, you can construct other interpolating polynomials with higher degrees, but there's exactly one of them that will work for a given data set of smallest possible degree. Next, it's possible to write out a closed form formula for this interpolating polynomial p. This is called the Lagrange form. The logic of it is perfectly straightforward, but it's very awkward to work with. We then discovered that we can also write this interpolating polynomial in the following form. We will have some constant plus another constant times x minus x0 plus another constant times x minus x0 times x minus x1, and this will continue until we have a constant times n of these x minus a constant factors. It would be n minus 1 if I started counting there, but then there's the nth factor here. We also discovered that a0 is the polynomial of degree 0 that interpolates the data set only at x0. a1 is the lead coefficient of the interpolating polynomial that interpolates at x1 and x0. a2 is the lead coefficient of the polynomial that interpolates the function at x2, x1, and x0, and so on and so forth. The thought here is perhaps we can have a recursive way in which we can generate these a coefficients in some manner that's reasonably easy to do. I'm going to invent a new notation. These numbers are called the Newton divided differences. I'm going to have the name of my function, a square bracket, and then a number of x values from my data set whose indexes are contiguous. I plus 1, the next one would be I plus 2, I plus 3, up till some ending value, x number L. This is going to be the lead coefficient of the polynomial of smallest possible degree that interpolates at xi plus 1 out to xl, though possibly at no other x values. We derived something called Neville's method and then never used it for anything. The purpose of doing Neville's method was to derive this recursion. Suppose I know the lead coefficient of the polynomial of minimal degree that interpolates at xi through xk, and also I need to know the lead coefficient of the polynomial that interpolates at xi plus 1 through k plus 1. These indexes are all exactly one smaller than these indexes. It turns out, through a long argument, that the lead coefficient of the polynomial that interpolates at xi all the way out through xk plus 1 is the divided difference, the lead coefficient, based on the larger indexes minus the divided difference based on the smaller indexes divided by one of the x numbers minus another of the x numbers. This will be the x number with the biggest index in the collection I'm thinking of at the moment, and this will be the smallest indexed one. When we organize this in a table, it'll be very easy to keep this straight. As an illustration of this method, I'm going to do an example that has 3 data points in it. x0 f of x0 will be 1, 6, x1 f of x1 will be 334, and x2 f of x2 will be 457. To organize my calculation, I'm going to write down columns of numbers of the same type. So firstly, I'll write the x's down, including their labels, the x0 label and x1 and x2. In the next column, I'm going to write down the function values. As with the x's, I'll put in their literal symbols, except I'm going to do something that indicates where we're headed with this. Each one of the function values is the lead coefficient of the polynomial of degree 0, constant polynomial, that interpolates the data set at that single x value. Each function value is an f bracket number that only depends on one of the x's. And here's the key thought. I know the lead coefficient that interpolates only at x1. I also know the lead coefficient of the constant polynomial that interpolates only at x0. These indexes are the same, except one of them has been bumped down 1 from the other one. It should be possible to use these two pieces of information to figure out what f bracket x0, x1 is. In an exactly similar way, it should be possible to use these two pieces of information to figure out what f bracket x1 and x2 are. So let's suppose for a moment that we had done such a thing. It's very convenient to write them in the following format. Each new column of numbers that I'm going to get will start one row further down than the previous one. This will be calculated by using that number and that number in some way. This will be calculated using this number and that number in a similar way. Once we have figured out what f bracket x0, x1 is, and f bracket x1, x2, you'll observe that the indexes involved here, the 1 and the 2, are precisely what you get when you increase the indexes 0 and 1 by 1. It should be possible to use our formula again to take those two pieces of information and figure out what f bracket x0, x1, x2 is, and by doing that, we will have the lead coefficient of the polynomial that interpolates at all 3 data points. After we do this, this number is going to be the first term in the Newton way of writing the polynomial. This number is going to be the coefficient of the term that has x minus x0 in it. This is going to be the coefficient of the term with x minus x0 and x minus x1 as factors. So all we have to do is calculate three numbers. If it doesn't cost us much effort to do it, this will be excellent. I'll calculate f bracket x0, x1. This is a divided difference based on two of the x numbers, which means in my reduction formula, I need to know two divided differences, one based on the larger of the two indexes, 1, and the other the smaller of the two indexes. According to our idea, we're supposed to take the divided difference that goes with the bigger index minus the smaller one, divided by the biggest x in the current collection minus the smallest indexed x. You end up with 34 minus 6 divided by 3 minus 1. 28 over 2 is 14. It cost me two subtractions and a division to do this. Calculating f bracket x1 comma x2 is done in an exactly similar way, resulting in 23 for an answer. To obtain the last one, f bracket x0, x1, x2, I'm seeking a divided difference with three of the x numbers in it, meaning in my divided difference formula, there'll be two divided differences, each one of which based on only 2 instead of 3. You write down the one that goes with the biggest indexes first, f bracket x1, x2, which we figured out a moment ago, minus f bracket x0, x1, which we have also figured out, divided by x2 minus x0, which is 4 minus 1. When the calculation is complete, the last remaining divided difference is 3. Again, the reason that all of these numbers are worth knowing is this: the 6, the 14, and the 3 are the coefficients of the terms in the Newton form, the interpolating polynomial. That polynomial is this first number, 6, plus 14 times x minus x number 0, x minus 1, plus 3 times x minus x 0, that's x minus 1, times x minus x number 1, which is 3. The fact that there's a 3 in two different places means nothing, it's just a coincidence. As a check to make sure our work is right, I can take x0, x1, and x2, that is to say 1, 3, and 4, and evaluate this polynomial for those x values and make sure that I get back 6, 34, and 57 as I'm supposed to. Obviously, if x is 1, if x is equal to x0, then this term is 0, so is that. The only thing that amounts to anything is the 6, and I am supposed to get 6 back for a function value. If I evaluate p at x1 at x equals 3, I'll get 6 plus 14 times 3 minus 1 plus 3 times 3 minus 1 times 3 minus 3. This term is 0. This is 14 times 2, which is 28. 28 plus 6 is 34, and we are supposed to get 34 for an answer. If I evaluate the polynomial at the last remaining x number, x2, which is 4, I get 6 plus 14 times 4 minus 1, plus 3 times 4 minus 1 times 4 minus 3. After the dust settles, it turns out that that equals 57. We're supposed to get 57 for an answer. This is the general pattern of how we're going to do the Newton divided difference table. This will give us the coefficients of the interpolating polynomial. Also, it writes it out in a form that's fairly easy to evaluate. We'll have to look at a couple of issues later. How to code this up, how to automate this process. And secondly, how will we evaluate the polynomial once we have these coefficients in hand? I'm going to stop there. I wanted this to be a very quick summary of how to do Newton interpolation. We have a couple of other issues that we can look at, but I'm going to put those in a separate video. In the meantime, I hope everybody has a good day. I'll talk to you again soon.